inverse functions, when they exist, can be tricky to work with. However, it turns out that inverses play surprisingly well with derivatives. Let's start with some geometric intuition. If f is invertible, then the graph of f inverse looks like that of f, except it's reflected in the line y equals x. For example, if the blue line below is the graph of f, then the graph of f inverse looks something like this. Okay, let's pick a point and draw its tangent line. And the tangent line to the inverse then looks like this. We want to see if we can relate the slope of the blue tangent to the slope of the green tangent. And the reason for this is that it's often very hard to find a nice form for the inverse of a function, even if you know it's invertible. But at the tangent level, we're just working with straight lines, so maybe we can avoid needing to find the inverse function and just work with the derivative of f. What would this look like? If the equation of the tangent line is given by y equals mx plus b, so that the slope m is the derivative of f, then the inverse line can be found by solving for x. That gives us x is equal to y over m minus b over m, and thus the slope of the inverse line is 1 over m. Okay, so if the slope of a line is m, then the slope of its inverse is 1 over m. Hopefully this holds for derivatives as well. Our theorem is then the following. Let's suppose that f is differentiable at the point c, f prime is continuous at c, and f prime of c is non-zero. In that case, there's an interval containing c on which f is differentiable, and the inverse itself is actually differentiable. Moreover, we have a formula for the derivative of the inverse function at the point f of c, given as follows. Okay, so there's a lot going on here. There are 3 hypotheses for this theorem, that f is differentiable, f prime is continuous, and f prime is non-zero, and there are a lot of results, that the inverse function exists, that it's differentiable, and a formula for the derivative of the inverse. This is a very non-trivial result, but there's a bright side. It turns out that this formula here at the bottom is actually pretty easy to find. If we start by supposing that the inverse exists and is differentiable, then by definition of the inverse function, we know that f of f inverse of x is equal to x. So let's differentiate this using the chain rule. Treating f and f inverse as separate functions, and using the fact that the derivative of the right-hand side is 1, we get this. Now we're looking for the derivative of the inverse, so let's solve for this to get the following. And while this might look different than what's at the top of the screen, it's actually the same if we plug in x equals f of c. Okay, so what does this win us? Let's use the above theorem to show that ln x is differentiable on the interval 0 infinity, and to find its derivative. Again, we're going to be able to do this because we know the derivative of e to the x, and ln x is its inverse. So to that end, let's set f of x to be e to the x, and f inverse x to be ln x. The range of f, and hence the domain of f inverse, is 0 infinity, so that checks out. And to apply the inverse function theorem, we need that f prime is continuous and non-zero. Well, check and check. Thus, per the theorem, we know that the inverse function ln x is differentiable on its domain, and by using the nifty formula above, we can find a formula for its derivative. We know that f prime of x is e to the x, and that f inverse of x is ln x. So plugging those in, and using the fact that these are inverses to one another, we find that the derivative of ln x is 1 over x. Now in that example, we knew what the inverse was. Let's look at something a little bit tougher. Here's a function f. Let's show that its inverse exists, is differentiable, and let's find the derivative of the inverse at the point 1. Now this function has been specifically chosen because you cannot find a nice closed form expression for its inverse, so we have no choice but to use the theorem above. We start off by noting that if we plug 0 into f, we get out the value 1. Since the inverse function switches input and output, we know that f inverse of 1 is 0. Now the derivative of f is this function right here, which we note is always strictly greater than 0, and thus in particular non-zero. It's also the sum of continuous functions, and so is continuous itself. This is what we need to apply the theorem, so we know that f inverse exists and is differentiable. Finally, we need to find the derivative at the point 1, for which we use our formula. We know that f inverse of 1 is 0, so evaluating f prime of 0 gives us the answer 1/2. Again, note that we never needed to find the inverse function, yet we're still able to find the derivative of the inverse function. That's exactly the power that the inverse function theorem affords us.